All right, we are about to crack a code that's hidden inside one of the simplest shapes you can possibly imagine, the right triangle. And believe me, this code is the key to a super powerful branch of math called trigonometry. So let's just dive right in.
I mean, think about that for a second. How can a shape you learned about in grade school be the secret behind something as mind-blowingly complex as GPS? It sounds almost like magic, doesn't it? Well, the answer is all in the secret language of triangles. And by the end of this, you'll know exactly how it works. So before we can even touch GPS, we have to start with a really fundamental secret that all right triangles share. It's a simple, but honestly a game-changing idea from geometry that really sets the stage for everything else we're going to talk about. Okay, this right here, this is the bedrock of everything. You probably remember the idea of similar triangles from geometry, right? It just means that if you have two right triangles and they share one other angle, let's say it's 30 degrees, it literally does not matter if one is tiny enough to fit on your fingertip and the other is the size of a mountain. The ratio of their sides will be exactly the same. That consistency, that predictability, that's the key that unlocks all of trigonometry.
So because these ratios are so darn consistent and reliable, mathematicians obviously had to give them special names. And we're going to learn them using a simple but incredibly powerful code, a mnemonic that has been an absolute lifesaver for math students for generations.
Let's start with the first piece of the code. SO. This stands for sine equals opposite over hypotenuse. Okay, so in trigonometry, we use that Greek letter theta to mark the angle we're focusing on. Now imagine you're standing right at that angle, theta. The opposite side is the one directly across the triangle from you. And the hypotenuse, that one's easy. It's always the longest side, the one across from the right angle. So the sine is just the simple fraction you get when you put the length of the opposite over the length of the hypotenuse.
Next up in our code is CAH. This means cosine equals adjacent over hypotenuse. All right, so what's adjacent? Well, it just means next to. The adjacent side is the leg of the triangle that's right next to our angle theta, but it's not the hypotenuse. So the cosine is the ratio between that side right next to us and the longest side.
And finally, we've got TOA. That's tangent equals opposite over adjacent. Now, this one's the odd one out of the main three because it doesn't even use the hypotenuse. It gives us the direct relationship, that pure ratio between the side opposite our angle and the side right next to our angle. So let's say it together. SOH CAH TOA. That's the code. Now, really quick, for each of those three main functions, there is a reciprocal, and all that means is you just flip the fraction. That's it. Cosecant is the flip of sine, secant is the flip of cosine, and cotangent is the flip of tangent. Here's a little memory trick that helps a ton. The s function, sine, pairs with the c function, cosecant, and the c function, cosine, pairs with the s function, secant. They just go together. Okay, enough with the theory. The real power of this code isn't just memorizing it, it's actually using it. So let's see how it helps us solve real problems, from finding some basic ratios to calculating actual real-world distances. Okay, let's take a classic 3, 4, 5 right triangle. Well, a triangle with legs of 3 and 4. We want to find the sine of angle theta, the one across from the side with length 3. So let's think. SOH CAH TOA. So, sine is opposite over hypotenuse. We have the opposite side, it's 3. But wait, we don't have the hypotenuse. No problem. Our old friend the Pythagorean theorem tells us 3 squared plus 4 squared equals 5 squared. So the hypotenuse is 5. Now we just plug it in. Opposite over hypotenuse. That's 3 over 5. And boom, there it is. The sine of that angle is simply 3/5. It's that direct. It's not just some random number. It's a relationship, a ratio, that's literally locked into the shape of that triangle. All right, let's try a more practical problem. Imagine a 12-foot ladder is leaning against a wall, and it's making a 60-degree angle with the ground. How high up the wall does it reach? Okay, what do we know? We have our angle, 60 degrees. We have the hypotenuse, that's the 12-foot ladder. And we want to find the height, which is the side opposite our angle. So which piece of our code connects opposite and hypotenuse? So it's sine again. So we just set up the equation, sine of 60 degrees equals our unknown height, h, divided by 12. You punch that into a calculator, do a little bit of algebra, and you get your answer. The ladder reaches about 10.39 feet up the wall. Think about that for a second. We just used a simple ratio to measure a physical distance without ever leaving the ground. Now that is incredibly powerful. But before we go any further, we have to talk about the #1 mistake people make when they first start using SOH CAH TOA. It's a really simple trap, but it's so easy to fall into if you're not paying attention to your point of view.
Here's the key. The labels opposite and adjacent are not fixed. They are totally relative. So from angle A's perspective, side A is opposite. But if you were to walk over to angle B and look from there, all of a sudden side A is right adjacent to you, and side B becomes the new opposite. The hypotenuse is the only one that never changes its name. So you always have to ask yourself, okay, which angle am I standing at right now?
So let's bring this all the way back home. We started with this kind of crazy question about GPS, and now we actually have the tools to figure out the answer. You see, this isn't just some abstract math for a classroom, it's the code that runs some of the most essential technology we use every single day. So here's where the magic really happens. Your phone gets a signal from a satellite way up in space. It knows the distance to that satellite, that's our hypotenuse. And it can measure the angle of that signal. So what do we have? We have an angle and a hypotenuse, and we can use that to find the opposite side. And which ratio does that? Our good friend SOCA. Your phone does this simple calculation with a few different satellites, and it triangulates your exact position on Earth. That little triangle is literally working for you, in your pocket, right now. So, the code is cracked. SOH CAH TOA isn't just a silly phrase to memorize. It's a tool for measuring the world. We used it to figure out the height a ladder can reach, and we used it to understand how GPS works. So my final question for you is this. Now that you have the code, what else could you measure? The height of a tree in your backyard? The width of a river? The possibilities are truly endless.